1995, question 3b, inclined plane, vertical landing, projectiles. So here we have a plane which is inclined at an angle of 30 degrees to the horizontal, and a particle is projected up the plane with an initial velocity of 20 meters per second at an angle of theta to the plane. The plane of projection is vertical and contains the line of greatest slope, and if the particle strikes the plane at right angles, then we have to find the angle of projection, and we have to also prove that if the angle of projection is increased to 45 degrees, then the particle will strike the plane obtusely and bounce back down the plane. So the first thing we want to do here is draw our diagram to show what is happening and mark in all of our angles on our diagram. So our inclined plane is an angle of 30 degrees. We have our particles projected up into the air with a velocity of 20 meters per second at an angle of theta to the plane. And then the particle lands at 90 degrees. So another thing to note then is when it's landing vertically, we know that there is no velocity in the x direction, and also that on landing Sy is equal to 0 because it started on the plane and lands on the plane, so the displacement in the y direction is 0. So let's make out our table and fill in our information for U, A, V, S and T in the x and in the y direction. So in general we would normally say alpha and beta, where U, our initial velocity, is U cos alpha in the I direction, U sine alpha in the j direction. And also we have 30 degrees there, so if we say sine 30, we know is a half, and cos 30 we know is root 3 over 2. So when we're filling in our table, we would normally say in the x direction U cos alpha, so that's going to be 20 cos theta. And in the y direction, that's going to be 20 sine theta. Now because it's the inclined plane, our acceleration in the x direction is normally minus g sine beta. But sine beta, well, is going to be a half. So that's going to be minus g over 2. And then in the y direction, we would normally say it's minus g cos beta, but cos 30 is root 3 over 2. So that's going to be minus root 3g over 2. So therefore, v in the x direction is u plus at. So that's 20 cos theta minus g over 2t. And in the y direction, 20 sine theta minus root 3g over 2t. S in the x direction is ut plus a half at squared. So that's 20 cos theta t minus a half of gt over 2 is going to become g over 4t squared. And in the y direction, it's 20 sine theta t. And again, half of root 3 over 2 is going to be root 3g over 4t squared. And our time is in terms of t. Okay, so now we have our table filled out. We have every equation we need for the question, and we're looking to find the angle of projection. So we need to look at what information do we know. So we know that it's landing vertically, and we know that on landing, Vx is equal to 0 and Sy is equal to 0. So both of those are going to allow us to find our time of flight. So we can find the time of flight when Vx is equal to 0, our time of flight when Sy is equal to 0, and we can equate them. And that will allow us hopefully then to find our angle of projection. So if we're letting Vx equal 0, our Vx is 20 cos theta minus gt. So by getting t on its own, that gives me 20 cos theta over g. Sorry, that should be g over 2. And therefore that should be 40. So we say this is our time of flight 1. And then we also know on landing, that sy is equal to 0. So you can either sub in your t into sy is equal to 0, or you can get your time of flight from sy equals 0, which is what I'm going to do. So we have 20 sine theta t minus root 3 g over 4 t squared is equal to 0. So if I multiply across there by 4, I have 80 sine theta t minus root 3g t squared equals 0. Taking out t as being common leaves me with 80 sine theta minus root 3g t. And then if I let both of those equal 0, I get t is equal to 0, or 80 sine theta minus root 3g t equals 0. And therefore my time of flight can also be written as 80 sine theta divided by root 3g. So now we have 2 times the flights, and we're going to equate them. Okay, so on equating there, we can see, can we simplify anything? So I can multiply both sides across by g, and I can divide both sides across by 40. So that leaves me with cos theta is equal to 2 sine theta over root 3. And then if I divide both sides across by cos theta, I'll end up with sine theta over cos theta, which is of course tan theta. And then multiplying across by root 3 and dividing across by 2, I have tan theta is equal to root 3 over 2. So because we're looking for the angle of projection, I then need to just get tan inverse of root 3 over 2, which then gives me an angle of 40.9 degrees. Okay, so now we have our angle of projection. We've part 1 done. So part 2 says prove that if the angle of projection is increased to 45 degrees, then the particle will strike the plane obtusely. So striking the plane obtusely means I can look for my angle of projection, or angle of landing. So we say that on landing, our tan of our landing angle is equal to minus Vy over Vx. But this has to be at the time of flight 2 only, because if we go back, time of flight 1 was from the vertical landing. But if its angle of projection has changed, then it's no longer going to land vertically. Whereas when we're looking at our time of flight for sy is equal to 0, well then that is the time of flight on landing, regardless of the landing angle. So if I get Vx, well Vx we said was 20 cos theta minus g over 2t, where theta is going to be 45 degrees. And our time of flight is 80 over root 3. Sine 45 over g. So therefore that gives me cos 45 is 1 over root 2. So we have 20 over root 2 minus sine over 45, again is 1 over root 2. Our g will go into g once. 2 will go into 80 40 times, and that leaves me with minus 40 over root 3 times root 2, which is root 6. So that gives me a velocity of minus 2.19 meters per second. And then if I look at Vy, well, Vy is 20 sine theta, so that's going to be 20 sine 45 minus root 3 over 2 gt, where our time of flight again is 80, and sine 45 we said was 1 over root 2 times root 3, so that's 80 over root 6 g. So simplifying here, we have 20 over root 2, and again g will go into g once, g will go into root into 80, so that's going to go minus 40 root 3 over root 6. So that gives me minus 14.14 meters per second. So of course now we can see we have our velocity in the x and our velocity in the y. And therefore if we're looking at tan of our landing angle, it's minus Vy over Vx, which means we're going to get a negative value for L. And we know that from our unit circle, the tan is negative in the second quadrant, but positive in the first quadrant. And therefore that means it must be an obtuse value if we're getting a negative value. So we end up with tan L is equal to minus 6.46, which is therefore obtuse. And we say because tan is negative in the second quadrant. So to conclude, we would say because it's landing obtusely, it therefore bounces back down. So it's always important with these kind of ones that you're giving a conclusion to get your full marks.